Hello everyone. In our last video we looked at double angle identities, and in this video we're going to look at half angle identities, and we're going to develop them and then apply them. We're actually going to be using two different forms of the identity we have obtained previously for cosine of 2a, this double angle identity, and we're going to use that together with a clever substitution later to establish our first half angle identity, which will be for sine. So if we start with cosine 2a equals 1 minus 2 sine squared a, we can always go ahead and move the negative 2 sine squared a to the other side to become positive, and we'll go ahead and move the cosine of 2a to the right. So we end up with this equation. Now if we solve this for sine squared a, we get 1 minus cosine 2a over 2. We apply the square root property, which tells us sine a must be plus or minus square root of this expression, which is 1 minus cosine 2a over 2. Now if we let this 2a here equal to x, then if we solve this for a, we get a equals x over 2. Now we're going to go into this equation and we're going to substitute a with x over 2, which we know it is equal to. And on the other side, where we see 2a, we're going to replace it with x. We use this kind of substitution in mathematics quite often. It's one of those things that takes a little bit of time to get really comfortable with, but once you do, you'll discover how powerful it is. So here's our first half angle identity, and it's for sine. So sine of x over 2 equals plus or minus square root of 1 minus cosine x over 2. Of course, for a given angle, we're going to get just one of those signs. So we will determine which sign depending on what quadrant x over 2 happens to fall into, or actually terminate in, is the proper way of saying it. So we're going to use another form that we had for the cosine 2a expression to obtain the half angle identity for cosine next. Make sure that you can obtain this half angle identity on your own without needing much help as we proceed. So now we're going to start with this form of the identity for cosine 2a. The process is going to be almost identical. So we're going to go ahead and solve it for cosine squared a. We move this negative 1 to the other side. We end up with 2 cosine squared a equals 1 plus cosine 2a. Of course, we switch the sides of the equation, which is always allowable. And then we go ahead and divide both sides by 2. So we end up with this expression. So we see cosine a equals plus or minus square root of 1 plus cosine 2a over 2. The fact that the relationship between these two is 2 to 1 helps us come up with this clever substitution. So we let 2a be x, and therefore a is going to end up being x over 2. Substituting in here, for a we plug in x over 2. For 2a we plug in x, and we obtain the half angle identity for cosine. So there's one more left, and that's tangent. We're going to come up with a half angle identity for tangent next. For that one, we're actually going to obtain 3 different forms. All right, so depending on which of the identities we've already established we start with, we get a different form for tangent. So just starting with tangent of x over 2 being just the sine of x over 2 over cosine of x over 2, which is one of the first identities we learned, that tangent equals sine over cosine. So now we just established that sine x over 2 equals plus or minus square root of 1 minus cosine x over 2. And we also established that cosine of x over 2 equals plus or minus square root of 1 plus cosine x over 2. So if we go ahead and put these under one radical, which we know from algebra we can do, we get 1 minus cosine x over 2 over 1 plus cosine x over 2. And if we do the far over near or outer product over inner product trick, the 2's will cancel out and we'll end up with plus or minus square root of 1 minus cosine x over 1 plus cosine x. So that's our first half angle identity for tangent. Now, if we use a different interpretation of sine of x over 2 and do the following, multiply the bottom and top of this equation by 2, so we end up with 2 sine x over 2 cosine x over 2 over 2 cosine x over 2 cosine x over 2. Now, right here, we had an expression from the past, which we know, if we recall, we have 2 sine theta cosine theta equals sine of 2 theta. So we usually see it going the other way, but you should be comfortable with both directions. So we can see that 2 sine x over 2 cosine x over 2 is going to be sine of 2 times the angle, which in this case is x over 2. And notice the 2's will cancel out, so we just get sine x. So this is what we're talking about here. We're saying 2 sine x over 2 cosine x over 2 equals sine of 2 times x over 2, as we were explaining over here. So we end up with just sine x on the top, and this is of course cosine times cosine of the same thing becomes cosine squared of that item, and we get cosine squared x over 2. Now we also know that, if you recall, one of the expressions that we had for cosine of 2x, or let's use theta just so they don't get confused, we had 3 forms for that, if you recall. But one of them was 2 cosine squared theta minus 1, correct? So if we solve that for 2 cosine squared theta, we end up with 1 plus cosine 2 theta. And now, of course, here we're replacing theta with x over 2. So let's try that here on the side. So we get 2 cosine squared x over 2 is going to be 1 plus cosine of 2 times theta, which in this case is x over 2. X over 2. So we get 2 cosine squared of x over 2 is equal to 1 plus cosine x. You see what I'm doing on the side here? This is what learning mathematics is all about. You don't want to leave any gaps. A lot of times when you're reading a textbook or something written by your instructor, like I have prepared here, there will be steps that will be skipped just to keep the textbook or the video or the PDF at a reasonable size. And of course, those details you're supposed to fill in for yourself. There should be no step involved where you look at it and you say, oh, I'm not sure how they got from here to here. No, you need to go and work it out, because that's the only way you're really going to master mathematics. All right, so notice on the top we have sine x, and down here we now have 1 plus cosine of 2 times x over 2, which, as we said, is just 1 plus cosine x. So here is a second form that we obtained for the half angle identity for tangent, sine x over 1 plus cosine x. Now, if you recall, we can get a third form if we do the following. We already know that the tangent of x over 2 equals sine x over 1 plus cosine x. So that's what we start with. Now we're going to use this conjugate trick that we have used several times in the various videos that we have watched together. And if we multiply the top and bottom of this fraction by 1 minus cosine x, we end up with sine x times 1 minus cosine x on the top. And this is in the form of a product of conjugates. Remember, f plus L times f minus L equals f squared minus L squared. And that's how we end up with 1 minus cosine squared x. Now, of course, we recognize that from our Pythagorean identity to be sine squared x. So now this sine x that we had on the top will cross cancel with this, leaving us just 1 sine x on the bottom. So one other last form that we're getting for tangent of x over 2 is 1 minus cosine x over sine x. So we'll summarize that in the next screen. So notice that we have 3 different forms for tangent of x over 2. These are all considered half-angle identities for tangent. One of them is plus or minus square root of 1 minus cosine x over 1 plus cosine x. The other ones include both sine and cosine. One is sine x over 1 plus cosine x. The other one is 1 minus cosine x over sine x. Next, let's go ahead and apply some of these identities we just learned to some actual angles. For our first application, we're going to find the exact value of cosine 112.5 degrees by using the identity we found for cosine, the half-angle identity. And of course, we know that if we take 112.5 and multiply it by 2, we end up with 225 degrees, which is one of the angles from the unit circle that we should know exact values for. So let's go ahead and bring in the unit circle. So if we start here, we know that here we had 90, 180, so 225 is right here in the third quadrant. So we know that it's related to the 45-degree angle in the first quadrant. And remember, we only need to memorize the values for the first quadrant because we can find all the others by adjusting the sign. So we notice that for 45, our values are square root of 2 over 2 and square root of 2 over 2. So here at 225, we're going to have negative square root of 2 over 2, and also the sign will be negative square root of 2 over 2 because both x and y values are negative in the third quadrant. So we also need to know where 112.5 itself falls, because when we use this formula, that's going to depend on the value of x over 2, which here is 112.5. We know 112.5 itself is going to be somewhere in the second quadrant, because from here to here is 90 and here is 180, so it's somewhere in this region. So we know that the signs are going to be negative for the x value and positive for the y value. So negative for cosine and positive for sine. So we can go ahead and start calculating the cosine of 112.5 degrees. And again, we know that the cosine will be negative. So when we apply this formula, we'll take the negative option. So negative square root of 1 plus cosine of x, which of course will be twice that, which will be 225. So 225 degrees over 2. So we get negative square root of 1 plus cosine of 225, as we determined, is negative square root of 2 over 2, and all of that over 2. So we end up with negative square root of 1 minus square root of 2 over 2 all over 2. And with the 1 there, we know that the easiest way to simplify such a complex fraction is to go ahead and multiply top and bottom by the common denominator, which is just going to be 2. So of course on the top we'll distribute, so both of those will get hit by 2, and here we're going to also multiply the denominator by 2. So we end up with negative square root of, notice that we have some cancellations here, these two will cancel out, so we end up with 2 minus radical 2 over 2 times 2, which is 4. And of course we can go ahead and split that up, since the square root of 4 is a nice rational number, so we put that over 2, and that will pretty much bring it to an end. So this is the exact value of the cosine of 112.5 degrees, and we obtained it by using the half angle identity for cosine. Once again, be very careful to look for the quadrant where x over 2 falls when you want to decide whether you should use positive or negative here, because a lot of students make the mistake of looking only for the quadrant of x, which will get you in trouble here. So make sure you can handle that on your own before we proceed. All right, so here is another half angle identity application. Again, I would like you to pause, go back and see which of the 3 different forms for tangent would be the most useful in this situation, and then come back and see if our approaches agree. And there may not be just one way to approach this, so your method may work just as well as mine, which may be different from yours. Okay, so we can see that if we take 157.5 and double it, we get 2 times 150 is 300, 2 times 7.5 is 15, so we get 315 degrees. Now we know that's actually one of the main unit circle angles. If we start here, go all the way around, that's 360, so 45 shy of that, we would be right there. So we're looking at the double angle x being here, so this will be where x is. Of course, x over 2 is the angle of interest. 157.5 again is going to end up being in the second quadrant, so x over 2 itself will be somewhere in here. So we're going to keep that in mind when we calculate items. And this time we're going to go ahead and use this formula. Again, I told you this is not unique. You may have used another one of the forms and that would work as well. So, but I'm just going to go with this one. So we get equals sine 315. Remember, if x over 2 equals 157.5, then multiply both sides by 2 and you get x must be 315 degrees. That's the algebraic reasoning. All right, so we get sine of 315 degrees over 1 plus cosine of 315 degrees. So on the top, for the sine of 315, which ends up right there, we know it's going to be, the cosine is going to be positive, square root of 2 over 2, and sine will be negative square root of 2 over 2, because the y values are negative in the fourth quadrant. So we end up with sine, which is negative square root of 2 over 2 over 1 plus the cosine of 315, which is square root of 2 over 2. Remember, the trick is to clear the fractions, not deal with them. So we're going to multiply the top and the bottom by 2. And on the bottom, we need to distribute. So each of those is going to get hit by 2. So we end up with negative square root of 2 over 2 plus square root of 2. Now, as you know, we don't normally like to leave answers like that with the radical in the denominator. We like to rationalize those for good practice, if for nothing else. All right, so we go ahead and multiply the top and bottom of this fraction by the conjugate of the denominator, which is 2 minus radical 2. And we end up with negative radical 2 times 2 minus radical 2 over, downstairs, of course, we have f plus l times f minus l again, which is f squared minus l squared. So we're going to get 2 squared minus square root of 2 squared. So on the top, we go ahead and distribute negative radical 2. So we get negative 2 radical 2 plus 2 over 4 minus 2. So we have negative 2 radical 2 plus 2 over 2. Now, if we go ahead and factor out a 2 on the top, that leaves us negative 1 radical 2 plus 1 over 2. Now we can cancel out these 2's, and we end up with negative radical 2 plus 1. You could leave it like that, but I think you'll admit that 1 minus radical 2 looks nicer. So we'll go ahead and leave that as the final answer. All right, so that's another nice application of half-angle identities. Make sure you're comfortable with the algebraic and arithmetic manipulations that we did. That's often what gets students. It's not the trigonometry. So make sure you're comfortable with this before we proceed. Okay, so here's another one. It's a little bit more interesting. There is definitely one form of the half-angle identity for tangent which is more efficient to use than the other forms. So I'd like you to pause the video, see if you can go determine which form that is, and then come back, see if we agree. Okay, I do hope you came up with this. There is a reason for that, and that's because of what's given. What's given is the tangent. And of course, we know that if we have the tangent, we also have, I'm going to pause for a minute, let you answer it for yourself. Okay, I think you guessed it. It's the secant, right? And if we have the secant, we also have, I'm leaving a pause for you to answer. Yes, we also have the cosine. And so because we can get the cosine out of this, we're going to go ahead and use this to figure out the rest, the tangent of the half angle. All right, so let's go ahead and take the tangent of beta equals negative square root of 5 over 2 and see if we can get the secant out of that. You know that tangent square root of theta, here in this case I'll go ahead and use beta since we have that, plus 1 equals secant squared beta. If you tend to misplace those, just start with your sine squared beta plus cosine squared beta equals 1. then just mentally divide both sides by cosine squared, and you get sine squared over cosine squared, which is tangent squared, plus cosine squared over cosine squared, which is 1, equals 1 over cosine squared, which is secant squared. So we have the following. We get negative square root of 5 over 2 squared plus 1 equals secant squared beta, and that's 5 over 4 plus 1 equals secant squared beta. So that's we can go ahead and just multiply top and bottom of 1 by 4, so we get 9 over 4 equals secant squared beta. Of course, remembering the relationship between secant and cosine, we know that this means cosine squared beta is going to be 4 over 9. So now we want to apply the square root property, but before we do, we need to be careful to make sure we choose the right sign, because we know the square root property says cosine of beta is going to be plus or minus square root of 4 over 9. So let's go ahead and bring in a unit circle now to see where we need to go. Now we're told that beta lives between 270 and 360, which 270 being here, 360 being here. So basically that's another way of saying beta terminates in quadrant 4, and we know in quadrant 4 cosine is positive because it's the x value. So here we're going to say cosine of beta equals the positive this positive square root of 4 over 9. So we get basically 2/3 for the cosine of beta. So now that we have cosine of beta, we're ready to go ahead and calculate tangent of beta over 2. So we have tangent of beta over 2 equals, all right, so once again, it's important for us to figure out where the sign of beta over 2 is, so that we can determine whether we're going to use the plus or the minus sign. And of course, if you notice, beta itself lives here in this region, but to find out where beta over 2 lives is easy, because we're just going to go ahead and divide by 2 all around. So we get 270 over 2, 360 over 2, so we get beta over 2 living between 135 degrees and 180 degrees. So we know 135 is right here, 180 is right there, so beta basically lives somewhere in here, beta over 2. All right, and that's what's important to us, beta over 2. Now, in this quadrant, which is the second quadrant, we know that sine is negative and cosine is positive. So tangent, which is sine over cosine, is going to be negative. So we're going to take the negative square root of 1 minus cosine beta over 1 plus cosine beta. So we end up with negative square root of 1 minus 2/3 over 1 plus 2/3. By now you know how to simplify those quickly. We're going to multiply top and bottom of this complex fraction by the LCD, which is 3. So of course we have to distribute, so we make sure all 4 terms get multiplied by 3. So we end up with negative square root of, notice the cancellations, these two will cancel out, these two will cancel out, so we end up with 3 minus 2, which is 1 over 3 plus 2, which is 5. And of course, we're going to simplify that. So we're going to write that as negative 1 over radical 5. And then we're going to go ahead and rationalize that denominator by multiplying top and bottom by square root of 5 over square root of 5. Finally ending up with the final answer, which is that tangent of beta over 2 equals negative radical 5 over 5, given that radical 5 times radical 5 is of course just 5. All right, so there's another excellent problem for you to practice. Make sure that you do this on your own if you haven't done so already before we proceed. All right, so here's another problem, and here we're given the cosine of 2x and a location for x, and we're asked to find the cosine of x. So you actually have some options here. So I would like you to think about it for a minute, see which formulas you think are useful here, and then come back, see if we agree. All right, as I told you, we have options here. Notice that we could be using a formula like this one, or we could be using this formula. They're both applicable here, but you have to, the way that you're going to use them will be different. Of course, given these two, I would always go with this choice because it doesn't involve any square roots. No guesswork, we can work that out more quickly. However, this is, after all, a half angle section. So let's challenge ourselves and do it this way, even though we know the other one is easier. All right, remember that if we're going to use this one, we're going to have to modify it a little bit, because the important relationship is that this angle is half of that angle, right? So as long as we keep that relationship, we can rewrite that one as cosine x equals plus or minus square root of 1 plus cosine. Remember, if this is x over 2, that becomes x. So if this is x, this becomes, I'm going to leave it for you to say, you guessed it, 2x over 2. So we're going to use it that way. So we have cosine x equals, now we have to think about the sign, so we'll bring in the unit circle again. Notice that x lives between pi over 2 and pi. So we know that pi over 2 is here, pi is here, so x lives somewhere in here. So we know that in this region, cosine is going to be negative, because the cosine of an angle is the x value associated with it. So here we're going to take the negative case of square root of 1 plus, remember we're using this form, so 1 plus cosine 2x over 2. So we're going to get a negative square root of 1 plus, we know the cosine of 2x is 1/4 over 2. Now you know what to do with that. Now we're going to multiply everything by 4 on top and bottom, and we end up with negative square root of, these will cancel out, so we get 4 plus 1, which is 5 over 8, which is, let's continue up here, which is negative square root of 5 over square root of 8, which will break up as the square root of 4 times the square root of 2. So we can bring out the largest perfect square out of there. So that's negative square root of 5 over 2 radical 2. Now it's easy to rationalize it, because all we need to do is multiply by square root of 2 over square root of 2. So we end up with negative square root of 10 over 2 times 2, of course, because square root of 2 times square root of 2 is 2. So we get negative square root of 10 over 4, just like that. Now, I did say we could have used this formula too, right? Let's verify. Look, we know what cosine 2x is. It's 1/4. So we have equals 2 cosine squared x minus 1. So we get 2 cosine squared x equals 1 plus 1/4, which is 9/4, because you have 1 over 1 times 4 times 4. Actually, we mean 5/4. And we have equals 2 cosine squared x. So we end up with cosine squared x equals, multiply both sides by 1/2, you get 5 over 8. So cosine of x, here we're going to apply the square root property, which means we need to know which quadrant x is in, but we know that. We know that x lives in here between pi over 2 and pi, so we know it's going to be negative. So we get negative square root of 5 over 8. And of course, we've done the rest of it here. So see the rest, and you'll end up with the same thing. So we get negative square root of 10 over 4. So here we had options, but since we were doing a half angle identity section, we went ahead and chose this as our main option for good practice. All right, and make sure you can handle both of these methods before we proceed. One of the best things you can do in mathematics for yourself to get real depth into all the interconnections is to go ahead and do this given problem with more than one method, if you know of more than one method to do it in. And that should do it for this problem. We'll go to another one. All right, we're getting near the end. That's the good news for you. So here what we're going to do is go ahead and prove two identities, and we'll be done for today. So here we're going to try to prove this identity. So I want you to give it a little bit of thinking as usual before you come back to watch the rest. See if you can in fact prove it on your own. I think that you'll be able to handle it. All right, so welcome back. So if we go ahead and start on the left side, we have cotangent squared of x over 2. We know that we can write cotangent as tangent, right? Of course, we would want to do that because we have a nice identity for tangent of x over 2. So we notice here there's a 1 plus cosine x and there's a sine x. So pause the video, go see if you can find the identity that works really well with that, and come back. Okay, I hope as you went on your journey, you did discover this identity that we had before that had exactly the elements we're looking for, sine 1, cosine plus. So let's go ahead and replace the tangent squared of x over 2. We know tangent of x over 2 is this, so we'll write sine x over 1 plus cosine x, and we'll go ahead and square that. So now that's tangent squared of x over 2. And of course, we know that that's 1 over 1 over sine squared x over 1 plus cosine x squared. And now we can do the outer over near trick, and we end up where we want to end up. And with that, we can go ahead and say QED, because that's exactly what we were trying to prove. All right, so that's a nice, quick little identity we verified. Make sure you can handle it on your own as we move forward. All right, here's the last problem we're going to prove tonight. I would like you to go and see if you can find the identity that's going to help us get this proof done, and then come back. Okay, I hope that was a relatively easy task for you, because we really only had one identity for the half angle of a sine. So we're going to indeed be working with this. So let's go ahead and start on the left side with sine squared of theta over 2. So we'll go ahead and write it as, we can write plus or minus, but we don't need to because we're going to be squaring. So we might as well just write one of them. So square root of 1 minus cosine of theta over 2. And we're going to go ahead and square that. So that's going to give us 1 minus cosine theta over 2. Now, we have the right form. Notice we need a difference and just one item on the bottom, and it looks like the only thing missing is a tangent down here. So let's go ahead and multiply top and bottom by a tangent and see what happens. So we end up with 1 minus cosine theta over 2 times tangent theta over tangent theta. So we get 1 minus cosine theta over 2. We can, of course, multiply the tangent in. So let's bring it in like this. And let's put the other one next to this one. So now if we distribute, we end up with tangent theta minus cosine theta tangent theta over 2 tangent theta. Can you feel it? We're almost there, right? So we get tangent theta minus cosine theta. Of course, we know tangent theta is sine theta over cosine theta, the whole thing over 2 tangent theta. So finally, we end up with tangent theta minus, these cancel out, sine theta over 2 tangent theta. And that's exactly what we wanted to show. So we're ready to say QED, which means that which was to be shown. Quod erat demonstrandum. It's from Latin for that which was to be proven. Okay, so that is that, and that should do it for us. Make sure you practice these and be safe until our next video.